this result is called the central limit theorem. Okay, so let's write that down. Okay, so for independent random variables and let's call them xi with mean mu and variance sigma squared, and Zn given as above. Okay, so notice that Zn here I've defined to be this, and notice here that Sn is just the sum from I equals 1 to n of xi. Okay, so for this I look at the sum of the random variables, I minus off the mean, and I divide by the standard deviation and also by square root of n. Alright, so looking at how, if I look at what sort of factor, when looked at this sort of square root of n ratio away from the mean, this error is given by. Okay, then the probability that Zn is less than some number, let's say z, as n goes to infinity, goes to a normal distribution. It goes to the integral from minus infinity to z, 1 over square root of 2 pi e to the minus x squared divided by 2 dx. Right? So as we're seeing, it doesn't matter what set of random variables I start with, if they've got the same mean and the variance and they're independent, I sum them up, okay, and appropriately renormalize, then that distribution looks like a normal distribution. Okay? So whenever I look at the error away from the mean, okay, provided I appropriately renormalize, then what I'm going to get out is a normal distribution. So this is sort of essentially the reason that normal distribution occurs so much. The perturbation of lots of errors, okay, gives a normal distribution. So think of it like this, for example, with the heat example. I mentioned that if you have a metal bar and you apply a heat at one point, then the distribution of the heat should be normally distributed. We could think of it like this, as there are lots of little sort of heat particles moving around, okay, transferring between the molecules in the metal, okay, and assuming they move around at random, okay, what we're going to get is from the central position lots of little errors propagating out, okay, given the eventual location of the heat that originally came from the source, okay. Now what that's doing is just adding up lots of small errors away from the mean, which is where it started from, okay. So that's why we anticipate that something like a normal distribution might be the distribution of heat as it spreads through that surface, okay. All right, so that's great and everything, but I probably haven't really convinced you why we get the kind of form that this specific form, why this function, why should we get, you know, the cumulative distribution function of a standard normal random variable, okay? So it's one thing to say that this is the answer, but the other, you know, I'm hoping I've convinced you enough that divided by square root of n is the right thing by analysing the variance, but it's not really clear why we get this specific functional form for the distribution that comes out, okay? So that's kind of surprising, okay? So I'll sketch essentially why that is, at least for this kind of binomial case, for when we're adding up coin throws. So sketch, and it is really a sketch, it's not a very rigorous proof, but I just want to kind of convince you why it might be true, of the central limit theorem coin throws. Okay, so let's let S2n be a binomial distribution with parameter 2n, okay, and probability of success at half. Okay, so if n is equal to 50, okay, we're looking at what happens to the sum of 100 coin tosses. How many heads do I get out of 100? Okay, so e.g. n equals 50 gives the number of heads from 100 coin tosses or throws. Okay, right. Now, so we know about the binomial distribution, so we know we can calculate the probability that S2n is the distance it is away from its mean. So we know the sort of the mean, the expected value of this is going to be n. Okay, we're going to ask about, well, what's the probability we get some error, k? All right. Well, we know the binomial distribution is given by the number of experiments, and then by the number of successes. So number of experiments choose the number of successes, okay, and then times the probability of the kind of outcome, number of successes, number of failures. In this case is a half, well, to the power of k times a half to the power of n minus k, right? And notice I can kind of scratch this out because this is just going to give me, overall, it's just going to give me a half to the power of n, okay? So let's look at this guy, okay? So let's investigate the likelihood of this error, okay, relative, okay, to the chance of no error. So what I'm saying here is let's look at the probability that we get an error of k relative, by which I mean divided by, the probability there's no error, so that's k equals 0. Okay, so let's investigate that guy. Well, what I'm going to be looking at is I'm going to be looking at 2n, choose n plus k, divided by 2n, choose n. And notice the half to the power of n's are all going to cancel out here. All right? So, well, what does that look like? Well, we've got 2n factorial divided by n plus k factorial here, and then n minus k factorial, that's what this is. And this is 2n factorial divided by n factorial times n factorial. Okay? And notice I can kind of cancel these guys, the 2n factorials I can cancel out. And that's going to cancel out with this. Okay? So what we're left with sort of n plus k factorial divided by n factorial and n minus k factorial divided by n factorial. Okay? So I could kind of write this out explicitly. All right? Well, let's look at this first term here. Okay, so let me just write this out a bit better. So it's n factorial divided by n plus k factorial times n factorial times n minus k factorial, right? So I can kind of expand this out. Notice I'm going to get sort of the first k terms, as it were, out of this, and then we're going to cancel out the remaining n minus k terms, okay? So that's what we get from this expression. We're going to get n times n minus 1 all the way down to n minus k plus 1. right? And all the remaining terms are going to cancel out with this n minus k factorial. Okay? And I can do the same here, right? I'm going to have all the terms, okay? If I cancel this out from here, I can get all the terms up to n plus k, right? So I start with like n plus 1, that'll be the first term that doesn't cancel out here, and n plus 2, okay, all the way up to n plus k, right? Okay, and now what am I going to do? Well, one thing I can do is I can sort of divide by n for each of these, right? So I can times and divide by n for each of the kind of k terms that are involved in either side here, right? So timesing and dividing by n, I'm going to get 1 for this guy. I'm going to get, and then dividing by the n here as well. So divide by n here, divide by n here is going to give me 1 plus 1 over n. Let's look at the next term here. I'm going to get 1 minus 1 over n. I'm going to get 1 plus 2 over n. Okay, and I keep on going all the way up to the top. I'm going to get 1 minus k, let's say minus 1 divided by n, and 1 plus k divided by n, right? Okay, so now what I'm going to do is I'm going to do a bit of an approximation here, alright? So one thing we can say is that, well, if I've got lots of sort of terms of this size, okay, I can do the following approximation, that sort of 1 plus x is approximately equal to e to the x for x small. Okay, why is that? Well, because if I look at e to the x, okay, the derivative of e to the x at 0 is equal to 1, and so its height is equal to 1, so I just get kind of a nice straight line here at 0. Okay, so look at 1 plus x, and e to the x, getting closer and closer to 0. Alright? Okay, so if n is really, really, really big, the error between these two is going to get really, really small. Okay? Okay, so a little bit of a leap of faith involved there. But the advantage of doing that is e to the x is a much more handy thing to deal with in terms of multiplication than 1 plus x. Alright? Really what I'm doing here is a kind of similar approximation to the one we did when we were looking at, for example, showing that 1 minus 1 over n to the power of n is approximately e to the minus x. Okay, so it's sort of similar vein to that approximation from earlier. Anyway, so if you can believe me that this is sort of going to be a good approximation for us, then I can approximate each of these terms. Okay, so here I'm going to get sort of e to the 0, then I'm going to get e to the minus 1 over n, all the way up to e to the minus k minus 1 divided by n. Okay, and then I'm going to divide it by e to the 1 over n. Okay, and this term e to the 2 over n. Okay, all the way up to e to the minus k divided by n. Alright? So now let's look at what this looks like. Alright? So sort of what this is really, okay, so if I kind of collect together terms, okay, and don't worry too much about the final remaining term here, is I've got sort of the exponential of minus 2 over n, that's sort of this collected together. Okay, well let me write it like this. Minus 2 lots of 1 over n, okay, that's this one and this one, okay, plus a further 2 lots of 2 over n, plus a further 2 lots of 3 over n, okay, all the way up to, and I'll do it up to sort of k minus 1 divided by n. Okay. Alright. Well, now, what I've got here is sort of the sum of numbers from 1 up to k minus 1. Alright? So I sum up 1 plus 2 plus 3 all the way up to k, or k minus 1 in this case. Alright? notice that this is approximately equal to k squared divided by 2. Why is that? Well, this is this kind of similar Gaussian argument from before. We've got 1 plus 2 plus 3 all the way up to k points here. Alright, and notice we're sort of essentially constructing a triangle. Right? So the sum of these terms should be roughly equal to the kind of square, okay, well, the area of the triangle, which is the square of the length divided by 2, right? So this is approximately going to be equal to e to the minus k squared divided by n, right? Okay, so there's various kind of errors and things that we're getting on here, but notice we're getting something that's roughly of the correct form here, right? We're going to get something that's going to give us sort of e to the minus sort of almost like x squared here, right? Another thing we can notice, so that's sort of giving us the sort of kind of some what we've kind of noticed there. So you have that roughly speaking, if we look at the error and ask if we're going to get an error of size k out of 2n coin tosses, it's going to be the sort of relative error between those two, sort of e to the minus k squared divided by n, right? Roughly, okay? Where this is going to get more and more exact, the bigger and bigger we let n get, okay? Further, we can look at the probability of that we get exactly the right amount, okay? So exactly hit the mean. So I want to kind of look at this, times this, and so I want to evaluate a little bit how this behaves. Okay, so what we're looking at is 2n, choose n. Okay, now we can kind of look at this guy, alright? Notice it's 2n factorial divided by n factorial times n factorial, okay? And now, sort of, what I'm going to claim, all right, is that that sort of essentially, I'm just realising I'm forgetting my 2 here. 2, okay, sorry. Okay, the 2 because we divide by 2 for the triangle here, right? Okay. By applying our Stirling's approximation, okay, so remember n factorial behaves like 1 over 2 pi n e to the minus n, okay, n to the power of n, right? So if we look at this, well, we can do the substitution, I suppose. I might make an error, I haven't done this calculation in advance, but okay, so notice I'm going to get 2 pi 2n here for the top one, e to the minus 2n, oh, I see what I've done, okay. So look at the probability of this, so I need the half to the power of n here, and here I've got half to the power of n, okay. Okay, good, I'm doing this explicitly, to the power of 2n. Okay, so applying that Stirling's approximation applied to this part, and I'm going to get the square of n factorial, because I've got n factorial times n factorial, so I'm going to get square root of 2 pi n, n to the n, e to the minus n, squared, because there's 2 of them, and I'm going to times it by a half to the power of n. Okay, so now let's have a look at what happens with all of that. Half to the power of 2n. 2n. Let me just check I've got that right up here as well. No, because remember I've got 2 to the n coin throws here. I'm going to get 2 to the n here. Okay, that's fine. Okay, apologies. Right, okay. So now I can basically look at cancelling out the various terms involved here. Right, so the easiest ones I'm going to get notice that the e to the minus 2n is going to cancel out with this e to the minus n squared here. Right? Notice the 2 to the power of 2n is going to cancel out with this 2 to the power of 2n here. It's going to get rid of that guy. Okay. Notice that I've got n to the power of n squared, which is going to cancel out with this n to the power of 2n. Okay, so that's going to cancel out with that guy. Okay. So all the kind of big terms have essentially cancelled out. What I'm left with, all right, is a 2 squared, okay, which is going to cancel out with this 2 squared, square rooted, so that's going to cancel out with that, all right, and then I'm left with square root of pi n divided by square root of pi n squared, all right. So the only things that are going to survive out of all of this is square root of pi times n. Okay, so sort of magically, all right, the only thing that's going to survive for the middle is something of the order of 1 over square root of n. Okay, now that seems a little bit magic, but it sort of makes sense because we know that the sort of width, the variance, okay, is telling us that there's a standard deviation of about square root of n. All right, so if you're expecting most stuff to be within square root of n, all right, so the width of being, or the probability of being within the square root of n, well then the height of the probabilities need to be about square root of n, otherwise we're not going to get something that's going to give us an area that adds up to something like 1, okay? So it sort of makes sense that that's the right sort of order of magnitude out of this, though it does look a bit magical the way everything sort of cancels out nicely, all right? So now we can kind of start to put everything together. Notice that if I want to analyze the following, the probability that the error that I'm considering, so that's the sum of these away from the mean, okay, divided by square root of n, okay, times the, or square root of 2n, okay, times the standard deviation of this guy, which is a half, okay, so this is exactly the term that we're considering up here in the statement of the central limit theorem, okay, exactly that, okay. And what to ask about this, right? So I'm asking exactly about this guy here, probability that this is less than some value z, all right? I'm actually looking at it less than some value b, but also bigger than some value a, right? Well, really, that's just the sum of a bunch of values of k, all right, which fit between b lots of square root of n divided by square root of 2 less than a lots of square root of n divided by 2. Notice if I just multiply this up here, multiply this up here, okay, and I'm looking at the probability that Sn equals n k plus k, right? So if I sum up the values of k, right, between here and here, right, and it's the same as summing up these values here, right? And now I can express that. So this is equal to that same summation all right, but I can look at it as, well, the probability this is equal to n times sort of the relative value of this error compared to if it was exactly equal to the mean. Okay. All right. And I know this guy is 1 over square root of pi times square root of n. Okay. Right, and I know this guy from up here is about e to the minus x squared, e to the minus k squared divided by 2n. Alright? So in other words, what we get is that this is this sum times 1 over 2 pi, I'm going to slightly change this expression here, e to the minus a half k divided by square root of n squared. Okay, slightly changing this expression. I've just need to add back in, okay, my square root of n, 2 over square root of n here. Okay, oops. Right. Now, okay, so now let's look a little bit at what this expression is sort of really saying. All right. Well, in some sense what we're doing here is we're looking at the function, that phi function. So if I do x here and I did phi of x, where phi of x is the probability density function of a normal distribution. Okay, so remember that's e to the minus a half x squared divided by square root of 2 pi, right? Essentially what we're doing here is we're breaking this up into little kind of intervals, okay, which have a width of about sort of noticing that that should be, I think this should be like that, so my apologies. Oops. So note, so what we're doing here is we're sort of splitting this into intervals, of each of which has got a length of about 2n square root of pi. Okay, and we're sort of summing up these rectangles that are about this width. Okay, so we're sort of taking all the rectangles between here, okay, B and A, okay, and we're splitting it into rectangles of about size 2 divided by square root of n, right, and then summing up all these heights, and the height is this, okay. So that's exactly what this summation is doing. Okay, so that's sort of the width of the rectangle. Okay, and that's sort of the height of the rectangle at that value of k for each, where k is the kth rectangle. Okay, so in other words, we're kind of approximating the area of this by a bunch of rectangles. Okay, we know as we're going to let those rectangles get smaller and smaller, this is going to get closer to basically calculating the area under this curve. Okay, so as we let n get larger, this is going to get closer and closer to doing an integral between a and b of this function. Okay, so essentially what we're doing is kind of approximation of the area under this by lots of little rectangles. So we're sort of doing a Riemann approximation, a Riemann integral approximation for this integral over here. Okay, so it's a little bit of a tough argument that, but there are some kind of simple steps. So one is our Stirling's approximation to get these square roots of pi's out and this square root of n, okay, which we know is going to happen anyway from the variances. Okay, and then this other trick, we kind of replace this with an increasing sequence of terms, and that's sort of the reason why we get this e to the minus x squared out of the normal distribution. Okay, or at least that's one interpretation of why that comes out. Right, so that gives us a rough idea of why the normal distribution sort of crops up. Okay, The actual proof of the central limit theorem is far slicker than this argument. This is sort of a nuts and bolts, sort of quick and dirty proof, okay, or sketch argument. Obviously you can see there's a lot that needs to be tidied up to make this properly rigorous, but I hope it sort of puts across the main ideas that are involved, okay, and why these sorts of terms come up in the central limit theorem. Okay, great.